use the word degree because I know that even though AI has become very successful, AI cannot be argued to have done 100% what human can do, but we have gone to a very reasonable extent. And recently, we can broadly differentiate AI into generative and predictive. So when we say AI is generative, we are talking about three popular categories. We're talking about the GAN, which is generative adversarial networks. In this place, we are talking about a network that have two things, a generator and a discriminator. So in generator is creating the sample, while the discriminator is trying to confirm the authenticity of the sample. So it is usually used in things like image synthesis, video game graphics. The transformer models, which everybody is becoming used to nowadays, it leverage the attention mechanisms, and is popular with chatbots, translation services. When you type in one language and you want to see the translation in another language, and LLP. Then we have the autoencoders. You are going to see an example of encoding in one of the practical research we are going to practical demonstrations we are going to do. But remember that in encoding, you are using something to represent the actual, such that when you move it to the other side, the other side, we also have a method of removing that thing in order to discover the actual. So on this side, when you are putting something to represent something, you are calling it encoding. While the other side, where you are trying to use an agreed method to remove the veil and see the actual, you are calling that decoding. But most of the examples I'm going to use today are going to be more of predictive AI. And some of the examples of predictive AI is regression analysis, classification, and time series analysis. In the second class of today, when we are going to do root cause or anomaly detection, we are going to see examples of classification types of research, because they are the most popular type of research you want to use when you are trying to do classification. Because what is classification? Classification simply means that you are trying to put every data point to where they belong. So that's why it is popular with spam detection, for example. If you are using in spam detection, for example, you are simply saying, this mail is a spam, this mail is not a spam. So that is classification. In medical diagnosis, for example, you are saying, oh, this person has cancer, this person does not have cancer. That is the kind of thing you are trying to do. But in the regression analysis, you are trying to forecast, you are trying to use the past event to stipulate what can happen in the future event. I also want to tell us that regression is not new. It's just that regression in AI is regression has always existed. If you have a lot of guys who are in statistics, humanities, economics, econometrics, they will tell you they can do a lot of regression even without writing any AI code. And when I did my MBA, for example, I did a lot of regression, but I didn't use any AI code to do it, because there are other ways of doing the regression even without using AI. So we have answered the question, what is AI? Then we need to answer the question, what is physics AI? When can we say that an AI is physics? Simply put, when you integrate a physical law or a physical constraint or physical principles into the learning and decision making of an AI, then that AI is now physics AI. Let me break it down in simple English. In a simple English, it simply means that if you are not only relying on data, you are not only relying on the pattern of data. Remember, in this type of AI, this in generative, you are trying to use data samples. In transformer model, you are also handling long range of dependencies in data. In variational encoder, you are trying to transform the input data and you are trying to recreate and to another data for representation. When we came to predictive, we were trying to use a continuous input variables of data to suggest what can happen in the future. In classification, we are receiving data and we are using that data to say, this is this, this is not this. In time series as well, we are looking at data in terms of timestamp, and we are saying, oh, this data, the way it is behaving, it is going to project to be up or going to project to go down. So there's an element of data to watch a pattern and take a decision. But in physics AI, we are departing from learning patterns from the data only. We are now saying, how about the equation? How about the characteristics of that situation being factored into the learning of the machine learning? So instead of saying, I am looking at the money spent for the whole of this year to project what money will be spent next year, I am now saying, is there an equation that can be used to summarize how money can be spent? So that if we have an equation that have all the constraints of how money can be spent, can we use that, embed it in an AI, so that the AI study the equation, generate data based on the equation, and use that data to interpret models, to forecast or to classify or to do whatever. That is what we mean when we say physics AI. And it can come in different ways. It can be a physics-informed neural networks. It can be a reinforcement learning that have a physical laws embedded. It can be an AI-guided scientific discovery. It can be a data plus physics hybrid AI models. At the beginning of this research, the most popular field were on fluid dynamics, climate forecasting, quantum chemistry, autonomous robots. But nowadays, physics AI have now gone to every other field, including smart grids. So today, I am going to be using the PINN in most of my example, just for the purpose of demonstration. And I'm going to also start with the fluid dynamics, then I will move into smart grid examples. So let's go. The first problem statement. Let us solve Navier-Stokes equation, which describe fluid motion without needing massive simulation. By the way, I got this from this website. This is a popular website that have so many examples of physics AI case studies. So the Navier-Stokes equation is used to describe the fluid motion. Now, in the past, people in chemical engineering, they will rely on the fluid motion data set, and then they will put it in the AI as an input, and then they will have the output. But now we can use the equation to work on AI. Let us see how it goes. So we go to the Google Colab. In order to save time, I have screenshot all my Colab into the PowerPoint so that it can be faster, so that I will not be logging, I will not be stopping sharing and returning back. So here, the first thing that was done here is to install the necessary library, which is, in this case, it is DeepXDE. What is DeepXDE? DeepXDE is a library for physics-aware AI, and it is popular for partial differential equation. So this equation here is the Stokes equation. And then with this Stokes equation, we embed the Stokes equation. Then when we embed the Stokes equation, we convert our outcome in a range of -1 to 1. So we define a range that you continue to generate range of data from -1 to 1 using this equation. And then we save it in variable known as data. This become the input of this data set become the input of our AI. So which AI are we using here, for example? In this place, we are using forward neural network. But I will also encourage us to try any other neural network just for the purpose of understanding the class. So this is the forward neural network. I just gave an example of the features of that neural network, the number of layers, and then the activation function is TAN. I also know that you can also try another activation function. You can try sigmoid just for the purpose of learning. For me, what I do always is, since here I am not saying TAN is the best because I've not tested anyone, but I'm saying on your own, if you are going to repeat this on your own after this class, I want to encourage you to just remove this TAN, replace with another one, maybe sigmoid function. Then we have the glorious uniform, which is for initialization. So this gives you initialization. Then to compile the model, to compile the neural network model, we use Adam Optimizer at a learning rate of 0.01. And because I don't know how many times when it will converge, I just put the epoch to be 1000. It can converge before that, it can converge after that. So that is what I've done here. And I also want to give credit to this library. I got this library from this website. So I provided a website where I got the library. It's used for solving differential equation. And when this was run, we have this result. So within 1.1 seconds, it was able to solve that equation. Now, this doesn't make too much sense because we're not chemical engineers, right? So let's go to something that is closer to our field. And then this is just a visualization of another example. Here, I try to run the same thing. So what I did was, you see in this equation, function of x is equal to x times sine 5x. So instead of solving for Navier-Stokes equation, I replace the equation with a function of x equal to x dot sine 5x. I also got this equation from this website. And then I try to visualize the training test and test. Of course, you can see from this result that the performance is not wonderful because I didn't bother to fine-tune the neural network. I just want to use it to demonstrate how nowadays people can comfortably generate range of data, do a lot of things on neural network even without having a data set. All that was needed just equation. So this equation is the physics of that situation. And because you have used the physics of the situation to generate your data as an input to your AI, we refer to it as a physics-aware AI. Okay, now another example. Assuming you want to do the same thing for RC circuit. We all know RC circuit. RC circuit is a resistor capacitor circuit equation. So if we want to implement on this equation is known as analytical solution. So if we want to do this and have data on a range that obeys this particular RC circuit, what are we going to have? So the first thing you are going to do, like I told you, you are going to install your libraries. You are going to import the necessary libraries for your work, and then you define your physics. Then your physics will generate data set that will become the input of your AI, and then the AI will now become the basis for carrying out whatever you are trying to do. So we define the PIN, we define the loss function, we train it, the model, we plot our results. On your own, also, I want to encourage you, since if you can do with RC, can you also try on your own with RLC? You know L is for inductor, right? So in the equation, in the last slide, some of this came up. The SCIPY, which is a Python library for scientific computing. So in this allow you to do things like optimization, equation, integration, and signal processing. IVP just simply means initial value problem. So initial value problem is IVP. Tensors are simply multi-dimensional arrays, like NumPy arrays. They are used in PyTorch, and TensorFlow to take to change your data type. So, and then you can also define your data type by different floats. FC here stands for fully connected in that equation. So let me go. So this is the output, but before this output, let me share the code. So the first thing we did here was to install the NumPy. And I've told you yesterday, I said whenever you see if you are new to AI or whatever, whenever you see Matplotlib, know that very soon we're about to draw something or have a plot. So we put the library for solving the equation. Then it's successfully done. Then the next one, we import the necessary libraries that will help us to work, the neural network, the initial variable problem equation. Then I now put the physics. So this is the physics. So I put the physics equation. Then I put it in the range of -1 to 1. I want to have a range of values from -1 to 1. Then we now solve the equation and then make it an input into our neural network. So the first, second, and third layer, I just put these various values. So what happened was that when I was preparing this class, I just tried 16 and then the result was bad. So I changed it to 32 because I'm not trying to promote any particular AI. So I keep on playing around figures. So I also encourage you, how about playing around with these layers and try to see the various outcome. And then maybe we can also bring out some new lessons from whatever you're going to have as your results. So we model it and then we produce the output. And then this is the outcome of the result. But I always like to see my result in a visualized form. It's better appreciated in a visualized form. So to plot that, I use this code to do the plotting. And then we have something like this as the output. However, you must have noticed something here. Because I didn't bother to fine tune, I didn't bother to optimize, the result shows that the prediction is flat compared to the real behavior of the ROC, which is supposed to be, if you study ROC in the physics textbook or electrical, you see that this analytical solution, dotted blue line, is supposed to be the perfect behavior of the ROC, whereas the PINN prediction is flat, which shows that these model parameters are not giving us a good result. So what do you do to get a good result? You just keep fine tuning. You keep making it better or try another model. So after making it better and fine tuning, like I told you, in fine tuning, I must be sincere with you. I was just, I kept adjusting and then I got something extremely perfect, which is not too good also, because this is like almost like an overfit. You can see that it just perfectly on top of the analytical solution so that you cannot even see the analytical solution. But that is one of the outcomes of when you do your fine-tuning properly. But I don't expect in reality, I expect that in reality, you're not going to have a perfect result. What happened was, because I was practicing before this class, so I tried to present the most perfect one, but It's not always the time. It's not always every time that it has to be as perfect as I have presented it here. But what I'm trying to say is that there was a reason why this result was not good. 3 reasons. 1, weak neural network architecture, poor gradient computation, and insufficient training on learning rates. So I try to work on these 3 categories, changing until then we have something better before and after. Okay, so let us see whether we can also, we have done on Navier-Stokes equation. We've tried it on ROC circuit. Can we also look for any example within the smart grid? So here we look at smart grid problem from PINN perspective, and then we remember also professor in one of the class, he was explaining about that most modeling of grid is an optimization problem. And if grid is an optimization problem, then it means that we can use a optimization physics equation to become the physics behind the grid. So if we can have the physics behind the grid to be an linear programming problem, then if we can get an equation that is representing the grid, then we can use it as our input to our PINN, and then we can say we have comfortably used a physics-informed AI for grid. So what did I do? The first problem statement, to optimize the power flow in a smart grid. So I now say, okay, we are going to solve the optimal power flow problem using power flow equation, such as the Kirchhoff law and the Ohm's law. To do this, I searched the internet and I was able to get another Python library known as PYOMO. So PYOMO is an optimization library that can help you to solve equation problems in Python. And to do that, the first thing that was done was to install the dependencies, the necessary dependencies. Very, very important. So one thing I want us to understand is, as long as you are not developing your own AI, if you are using, because for me, my research interest is engineering applications of AI. So in my class, I don't teach students how to generate new AI, because I feel that there are so many AI tools that people are not even using. So why is everybody crazy about new AI when we have not even used the ones that are in existence? So my research interest is always about teaching people AI that are already developed. So if you are in my class and you are trying to learn from me how to develop a new AI, I'm sorry, I may not meet your needs. But if you are just interested in using what AI already developed by others, that is my area of specialty. So I always focus my attention on when any AI tool is out, I try to ask myself, oh, this AI is out, can I use it? That is my interest that's my own research interest, because I discovered that the people abandon a lot of things because they are pursuing new one. They want to have new one, new model, new code, new this. But the old ones are useful and they are serving very well. So why do you want to abandon them? So here, I also get this from the internet. I was able to get to install the PYOMO and then install the linear programming kit, which will help the PYOMO to work. And when that is done successfully, the next thing is we put the physics of the grid, and then we run the power flow equation code. So because of the case sample I gave, it gave for me the output of bus 1 to be 80, bus 2 to be 50, and bus 3 to be 30. And then because I love visualization, I said, okay, how about we visualize this? To do that, I use the network X, which I taught us yesterday. So the network X, I was able to use it to visualize that output. So to do that, we'll install the network X again, and then we bring the output of that result and make it the input of our network X, and then we draw something like this. So today, so you can see I have tried to use the PYOMO, generate the case studies of bus situation, get the output, take my Google, move to Network X, use my Network X to visualize the outcome. So another tool I also want to introduce to us is the PYPSA, which I also mentioned yesterday. So what I did here is I used the PYPSA to do smart grid simulation. Then I define a simple power grid and run the load flow. So what I did here in step 2, I went to ChatGPT and I said, give me a simple power grid and load flow situation. So the outcome of the ChatGPT, then I took it to my PIN model to now run PIN for resilience, and I'm going to demonstrate that. Then I test the AI model against grid failure. I visualize my results. So to do that, the first thing is to install the dependency for PYPSA, and then we now do the rest following the steps I've already outlined. So this is the code. So I do the 3-bus power system. I install the dependency. I put the PYPSA, NumPy, Torch, and the rest of them. Then I put this simple smart grid model that was given to me by ChatGPT, because I just say, ChatGPT, give me just 3-bus simple case study. Then with this becomes my physics. Then it becomes the input of my PIN. So I then train the PIN informed AI model to learn how the voltages will behave under changing loads. So you could see here my fully connected layer. Remember the last example, I used 32, but now I'm using 16. It doesn't matter. All I'm just trying to do is trying to run and then trying to see the outcome. Then this gives me the result. So you can see in this my result, I have the actual voltage power flow, the PYPSA power flow solution, which is 1, 0.9, 0.9. Then the AI predicted voltage. So when it was 1, my prediction was 1, which was okay. For 0.99 for bus 2, my prediction was 1 point something. So when it was 0.99, my prediction was 0.99 as well. So this second answer is the prediction of my AI. The first one is the actual output of the PYPSA. Now, what if I now will now put failure? In failure, I try to visualize what happened. So the dotted line is my prediction, while the blue line is the actual voltage. So you can see that the fully connected layer could not give a perfect prediction of, especially for the third bus, which also indicates the removal of one of the lines. So to generate failure, we run the PYC, we use the AI to predict, then we compare the actual and the, which is what I have done. So a repetition again. So these steps, the same repetition. Install the PYPSA, import your library, define your grid, and then put your physics AI as your input, add your battery, run the result to get your voltage output, both your PYPSA output and your AI output. And this gives us something like this after restoration. So before failure, the voltage was 1, 0.99, 0.99 before failure. Then after the restoration, we also have the results as this after the recovery. And then this is the plot of the after recovery. So trying to demonstrate a physics resilience scenario. So let's put my discussion in perspective. I'm saying that physics aware AI simply means you are recognizing the equation or the the law governing the situation, and then you are using that as a basis for becoming an input to your data for your neural networks. In this example, we use few forward neural networks, but it can be anyone. But the most important thing is that the moment your input is being influenced by the equation, like the my one of my recent paper is published on the physics aware AI for battery management system. So we in that paper we use the equation of state of charge, state of health of a battery. So I will now leave you with this question. What areas would you love to apply physics aware AI? So any area you want to apply that AI, the first thing that should come to your mind is what is the physics governing that particular area? Then how can the optimization techniques be used instead of machine learning to govern that particular AI? Then that can now serve as the basis. Another area I also want us to think about is what about explainability? If can physics aware AI also have some element of explainability? Of course, people also argue that since physics aware AI already have equation that was the basis of the decision, we can say that it is already having some element of interpretability. But interpretability and explainability are not always the same. And that is a topic for another day. So to also give you a very good material to read on this topic, our lab has published a very beautiful paper on physics informed machine learning for data anomaly detection, classification, localization, and mitigation, a review and a path forward. And also the second paper on decentralized modular nonlinear physics informed neural network for synchrophasor data anomaly detection. These two papers, they are very important, and they answered virtually all the questions that this class is trying to present. And I encourage anyone that have time to try to download and read any of these papers. So somebody said, I am transcribing this call with, oh, thank you. Thank you for that. Yeah, so let's take let's react to questions in the next 15 minutes. I want to, because I enjoy discussions rather than just talking continuously. So let's take discussions. Let's listen to people. Let's hear people talk. If you have questions, please you can ask your questions. And okay, yeah. So yeah, so I have the code for those who may want to who may have a need for the code. If you have a need for the code, I can always give the code out through the coordinators of this program.
Yeah, Dr. Cosmos, maybe you can put the
The codes are not
link.
mine. I also got them from the internet. I tweak them. I use
Oh,
Gemini to edit them. So if you need the code, I always free to give it out.
okay. I think Dr. Cosmos, you can put the link maybe in the chat, maybe if it is possible to put the link in the subsection here.
To put the what?
The link of your code,
Okay,
machine learning.
okay. So let me share the okay. Okay, so somebody's asking if physics-aware AI is the same as predictive AI. So now I will answer that question this way. Let us go back to the definition of physics-aware AI. In physics-aware AI, we said that the AI is receiving an input relying on the laws that govern the performance of that scenario. And then the law cannot be used to generate data, and that data become the input of the AI. Because the law was used to generate the data that was the input of the AI, we call it the physics-aware AI. Now, what is predictive AI? Predictive AI is the type of AI that rely on past data to explain the present or the future. What is generative AI? So it means that you cannot say physics-aware AI is predictive AI. No. Because there can also be physics-aware generative AI. There can be physics-aware predictive AI. So beautiful. Rahat Nas says it can be very helpful when we don't have enough data to train the model. Beautiful. That is a perfect explanation. So it's not about predictive AI or generative AI. It is about the absence of enough data. In fact, the physics aware AI became popular because people are becoming frustrated having access to genuine data. In our second class of anomaly, you are going to see what I'm going to say in that anomaly detection. Even me, when I was preparing my slide for this class, for the anomaly detection, I was frustrated. I was looking for data sets that can be but some labs, some students in some countries, they don't have enough money for research. I don't know about India, but for me in Nigeria, when I'm teaching my students, a lot of times I cannot teach my students. I can't do a lot of simulations because the equipment are very expensive. Sometimes you want to simulate, like yesterday, 2 days ago, professor was talking about if you want to do some digital twin projects, you need millions of dollars. Now, if you are in a country where you are doing a PhD and you want to do a smart grid of India and you don't have equipment to do it, but you have the equation that can be used to simulate the grid and generate as much data as you need. A smart professor, a smart supervisor will tell the students, let's go this way. Because we don't have the facility to buy this equipment, let's go this way. So physics-aware AI is a serious breakthrough in the era of lack of data or insufficient amount of data for training models. Thank you so much, Rahat, for that observation. Let me see if there's another question. So I have shared the Colab. If you are trying to access it and it's not working, please endeavor to send me an email, or you can contact the organizers. They can reach out to me. If the code I share with you is having problems, I will be very happy to assist in resolving the problem. Then the second one also, this one, let me also share this one. Yeah, let me share this one as well. Anyone with the link, copy the link. So I'm sharing another one for the one that was used to when we don't have enough data. Okay. So the second one is, the second link I shared is about the demo, the smart grid demo, where I did the demo. Another one is okay. So the third one, I will not share the third one until after my second class. So after second class, I will share the third link. After the third class, I will share the link. Then another thing I also want to explain here is in physics-aware AI, you also have to be careful if you rely on AI for debugging of your code. I give you an example. So yesterday, I was writing some code for Physics AI, and then when I run the code, it was giving me error. Then I just click on Gemini to help me edit. Now, Gemini edited my code, and then the code was working. But you know the problem? It changed my equation. So you have to be careful of hallucination. It's one of the challenges we have with the current implosion of generative, and we are in the world of hallucination, in the world where AI is trying to assist you, but AI successfully give you wonderful results that is not correct. You know, a good result that is not correct. So when I ran the code, it was working, but even though the code was working, when I checked the lines of the code one by one, I saw that it just changed my equation, and then the code worked very well. So if you are always relying on AI for editing your code, please be careful. Watch very well that your physics have not been changed, because if the physics of what you are doing have been changed, even if your physics AI result is good, it is no longer solving the problem. It is solving a different problem altogether. Now, somebody is asking, he says, is it possible to obtain state estimation values by creating using network X in Python? So let us remember what I told you about network X. I told you that network X will only help you to visualize. So you cannot use network X to get what you are looking for. You have to go back to OpenDSS, or yes, you have to go back to your OpenDSS or Mininet. Your network X, remember I told you why network X is always good for visualization. So it means that you would have already gotten an idea of the boss before you can use network X to visualize it. For state estimation, it has inbuilt for state estimation. Thank you so much, Rahat Nas. I think I have to contact this person. This person is really helping me in this class. Thank you so much, Rahat Nas, for the answer. So you cannot use network S for the state estimation. So use what Rahat Nas have said. Network S will only assist you in the visualization. Yeah.
I don't know.
Okay. Yeah, go ahead. Just deep.
Yeah. Good morning, Cosmo.
Good morning.
Thank you for the insightful presentation today and tomorrow. Today and yesterday even. It was really insightful. I actually have a query regarding making the process online. Like when you apply an algorithm, whether it is for detection, mitigation, or any other algorithm that we use in cybersecurity or in any other application, how can we make the algorithm or the procedure online? Like yesterday, you mentioned you do the simulation, then you collect the data sets, and then you load that data set in the Python or in any other Colab or whatever platform you're using. Can we make it online? Can the simulation and the Python basic platforms be connected, and can we make the process completely online?
Of course, it's possible if you can link your data set source. It means that you also have to make sure that you also have a repository online. Then if you have a repository online, then there's a way to link your Colab to your repository source online, which is, we are going to see an example of it in my next class.
Live simulation cannot be linked to Python platform. Live simulation, like if I do it in RSCAD, if I'm doing a simulation and I get some results or fault or something, can I link it to the Python platform? Is that possible?
Yeah. So what I'm saying is, is there a way to link your output data into a repository online?
Okay.
Once that is achieved, then your repository online can always be linked with the Colab online as well.
But there will be surely some time delays involved in the process.
Yeah, we cannot eat our cake and have it, right? We have to lose something to get something.
Exactly. So that's not absolutely online.
Yeah, we have to lose something to get something. So what I did in the next class, was to use I link my collab to UCI repository. You know UCI repository,
Mhm.
UCI machine learning repository. So we just link it. So I don't need to run the data set in my system. Just link it to the UCI repository, and then it collect the data set from that side and then run the work. But
Okay.
if you are working on physics, AI research, you're already online.
Yeah.
Yeah, if you are doing physics aware research, you're already online because you don't even need data set from anywhere. You're just generating your synthetic data with your physics equation, and then it's becoming automatically the input to your physics model. So indirectly, you're already online.
Okay.
Mm.
Thank you for your comments and your suggestions. We
Thank you
look
so much.
forward for such applications in the future lectures.
Yeah.
Thank you. Thank you.
Mm. So I will give 5 minutes break, then so that 9:25. I'm not sure there's any other question. Blah blah blah. Okay, there's no other question. So I'll give 5 minutes break, then we will start the next class.
Yeah, that's okay. Dr. Christmas, we can take a 5 minutes break and then.
Yeah. So if you have questions, just drop them in the chat. I have also dropped my slide. I hope it's helpful. If you have any problem or questions, please, you can always chat with the coordinator. Coordinators can always reach us.
Yes, yes.
Okay.
Yeah, I
Facilitator,
think participants, yeah, are back. Maybe we can start.
okay. Thank you very much. Welcome again, everyone. Um, we are going to go slowly and carefully and see that we all understand ourselves. I want to go to the second class, which is the AI-based, um, the AI-based anomaly detection. Whether you talk about security or anomaly detection or root cause, the point you are trying to make here is you are trying to identify that something out of the ordinary is happening. So the throughout this class, throughout this webinar, in the from last week until now, there is one point you would have understood that the grid is now a cyber physical system. So there is no longer a debate over that. And if it is a cyber physical system, then it is also going to be prone to cyber physical attacks. It is going to be prone to anomalous data generation. It's going to be prone to even innocent errors that will lead to wrong data being generated. It's not every anomaly that is about attack. It can also be a honest error. It can be a malfunction of an equipment or an existing facility. But the important thing is that you are going to see that there is something out of the ordinary. Because of that, you could see that even our own lab alone, in the last couple of years, we've written so many papers in the Smart Grid Lab, SGRA Lab, on different anomaly issues, synchrophasor data problem, threat detection in power grid network, classification of anomaly in power distribution using outlier, weighted least square. So there is no one size fits all. But what these arrays and numerous papers are confirming is that it is an interesting research area that also is attracting attention. But we need to understand some fundamental concepts in order to embrace this class. We need to differentiate certain issues, security. When we talk about security, we're talking about monitoring or preventing or stopping a breach or an attack. When you say resiliency, resiliency is not security. Resiliency is the preparedness to restore or the preparedness to sustain, to continue to exist in the face of disturbances, in the face of attack. Can we exist? Or even if we don't exist, can our critical site exist? Say, for example, if a grid is attacked and the city is thrown into darkness, can the power supply to the hospitals continue to exist? Can the power supply to some critical infrastructures that will lead to more colossal situations, can they continue to exist? If the grid have the ability to do that, then that grid can be described as to be a resilience grid. When we say anomaly, anomaly simply means out of the ordinary, something that is different. So if you have a bucket of white apple, and then you see one green apple in the middle, that green is, in terms of color, is an outlier. It's different from the other white apples. So we can describe the green apple as an anomaly from color perspective. However, if you are just referring to that bag as a bag of apple, it means that both the white apple, the red apple, the green apple is apple. So there is no anomaly because they are all apples, even though the colors are different. So when you say something is anomalous, you must have a basis and a threshold. So before you can say something is out of the ordinary, you must tell us what is your definition of ordinary. So when we have your definition of ordinary, then whatever is above or below what is your definition of ordinary can be referred to as anomalous. Then that brings us to intrusion. Intrusion is in unauthorized entrance. Detection is to spot or to identify. Classification is to put in groups. And the root cause is to investigate the why. What we call explainability in AI. The why. Why did it happen? So, in our lab, in the SG Rail, we came up with this some years ago on the detection guidance for cyber resiliency template. We look at if you want to do anomaly in malicious code detection or personal monitoring or network monitoring or impact assessment or data aggregation or event analysis, the things that are defined as ordinary under this perspective and whatever happens out of that definition of ordinary can be treated as an anomalous that have been dictated, whether it is in the network or event or aggregation or impact assessment or monitoring or personnel, because personnel can also cause issues. Security for grid is not only cyber, there is also physical security of grid. A typical example, in October 2024, in October last year, in my country, Nigeria, after the grid had a collapse of 2 hours, kind of 2 hours collapse of grid, and when it was restored, in one of the states, some group of people physically went and vandalized the equipment, and everybody returned back to grid collapse again in less than 2 hours after restoring the grid. So that was not a cyber attack. That was a physical direct attack. So personnel monitoring, staff monitoring, people monitoring, they are all part of grid support, and your ability to come up immediately after this happens showcase your level of resilience. But let us not limit our work to AI building block for anomaly detection, so that we cannot discuss everything, but let's just limit our discussion to AI. So basically, in the AI discussion of anomaly detection, we're just talking about getting your data set from either from the dataset repository or a physics-informed dataset, as the case may be, and trying to know defining what is ordinary, which is the base detector. And then based on what is ordinary, we can know the normal, and then we can know the abnormal. And then if we can know the normal and the abnormal, we can even go ahead to also classify the types of abnormality in terms of the extent of the outlier performance and the type of outlier. And then that will now give us definition of what is normal and what is not normal in that data set. For our lab paper where this diagram was gotten from, you can consult this link. So what are the causes of anomaly or challenges in the smart grid? Human errors, natural disasters, equipment failures, insider attacks, aging equipment and failures, enemy nation attack, which is not always popular, but it also happens, especially in times of war. Then interoperability issues can also cause anomaly. So these are various reasons and various motivating factors why research into this area have continued to be, and the research will continue because these situations continue to happen in different ways over the years, and so people continue research into this is never ending. And why is this so? Because a typical smart grid is actually a potential source of big data. There is data everywhere in the smart grid. There is a PMU data. There is a smart meter data. There are meter measurement and logs from different substations. And there are so many substations, especially for big countries like India, USA, Nigeria. These are big countries. Miles, there are so many miles and miles of substations and distribution. The distribution transmission miles to cover are so numerous. The countries, as they are big, they continue to generate data. And this also means that the research into data anomaly, data detection, data generation issues in smart grid is never ending, especially for big countries, India, USA, Nigeria. These are very large and big countries with so many data and so many substations. So in some typical countries, you can have this statistics were generated by Professor Anjan of Washington State University. He argued that just about fixed asset alone, we have 7,500 generating plant, over 75,000 substations, 300,000 miles of transmission lines, and 2.2 million mile distributions and of feeders, and more than 300 million customers using having access to the grid. And of course, in some countries we have competing figures like this, especially for large countries. So it means that there are going to be anomaly issues. For example, even in PMU alone, PMU data sets, for example, can be the data quality can be tested by statistical and data mining approach. It can be tested by the physics AI approach, which I've already explained, or conformance testing. But conformance testing requires that you have to do that in the lab, or you have to do that after installation. So, but in this class, we are going to focus on how do we do an aspect, not the entire work. So I am not, let me say something. I am not a smart grid expert. So let me put that in perspective. If you've checked my profile, you will understand what I'm talking about. I'm an electrical engineer, but not a smart grid expert. So most of my jobs, most of my work are AI for SCADA, AI for smart factory, AI for smart home, AI for intelligent vehicles, AI for smart space. So I am not just particular only about smart grid. It's not my research. It's not my expertise. So how can we now detect an anomaly situation in the midst of normal situation? And to do that, we need to ask ourselves, anomaly detection refers to as identifying data points, data patterns, data observations that significantly deviate from the expected behavior within a data set. So something you can say a rare event or a system failure or an error or an intrusion or an outlier. I prefer to use the word outlier. And there are various methods of doing this, the DBScan, the Chebyshev method, the maximum likelihood estimation method, the KNN, because in all these methods, we are trying to establish the closeness of something to something, and then you are not saying whoever is not close to this is an outlier. However, like I am always saying, I am a user of technology, so I try not to say this technology is better than the other technology. I promote usage, and that is my research area. My research area is usage. Just use. The reason for developing things are to use, so let's use. But if your research area is to promote one over the other, it's okay. But my research area is to keep using, just use. No matter how old the technology is, if there is a new way to use an old technology, I want to use it. So for me, there is no single winner. However, the anomaly can also happen when we have lack of training data. And then sometimes most times, not sometimes, most times we need to continue to improve our tuning efforts of the AI in order to continue to have a better performance and results. In most of the time also, when we try to measure the performance of our AI, we use popular metrics like precision, recall, and false positives, which example, in one of the publications from our lab, we try to compare linear regression, DB-scan, and the Chebyshev method and the maximum likelihood estimation ensemble, and then you have this final kind of result. You notice that here the ensemble have a better result. It's expected, and that is why I'm always careful not to say this is better than this. If it's an ensemble, the result is supposed to be better, because ensemble is like you want to fight a battle, and you said one person should carry a 50 kg load. In ensemble, you are saying 2, 3, 4, 5 people, let's come together and carry the same load. Of course, you expect that when more than one person come together to do something, they are likely to do it better than one individual doing it. And that is why this result is not surprising, that an ensemble method is performing better than the standalone method. And this is also a graphical demonstration of when something is an outlier, but this is not the focus. Let's go to the focus. First thing is, there are different ways if you are a student, because I can see in the comment in the group, I can see that some of you are PhD students, MSc students. So in my discussion, I'm always remembering that I'm also talking to students. And if you are challenged like myself, I used to be very challenged of not having access to equipment, the IEEE data port can also be your source of data set for some of the anomalous situations. Our lab also have some data set also published, which you can also use if you have problem of having your own data set. And so today I am going to rely on synthetic data set, and also I'm going to rely on UCI data set to demonstrate my work. And if you are using data set, there's one mistake. Yesterday, I rejected one paper in engineering applications of AI. And what was one of the reasons for that is that some authors, they just mention the data set they use for their research, but they do not show their knowledge of that data set. Now, if you are making use of a data set, even that you are not the one that generated it, you have to show that you understood that data set. And one of the ways to do that is make sure you read and understand the data set description and instruction. It is wrong to think that because you are doing AI, once you feed data sets, and then the result will be very accurate. It's not true. You must understand what you are feeding into your AI before you can understand if you are even doing the right thing or not. So in this, it's very important to do that. And then we move straight to practical session. So for our hands-on demo, which we are going to do, the first thing I did here was to load a synthetic data set using the random seed Python code to generate samples of data. Then I created a data frame as a CSV. Then we mount the CSV knowing the pathway. Then we use isolation forest to check for anomaly. Of course, in my synthetic, I also intentionally generated anomaly. So I wanted my isolation forest to be able to dictate if it can differentiate the normal one from the anomalous data, and then visualize my result. So let's go straight to the Google Colab. Sorry, I opened so many. I opened so many of my Colab, so I need to close. Okay. Let me explain this part. Then the next collab, I will show the next collab. So in this case, what we did was, if you have been following my class, you will be used to the beginning of this. Always bring your dependencies and your necessary tools you need. So in this case, because we are going to work with data, I bring my pandas and my numpy, and then I generated a random number of numbers using the random.seed. Then I gave myself 1,000 samples, and the 1,000 samples I try to generate anomaly sample by making sure that the probability of the anomaly is 0.95. Then we arrange the anomaly to be in, we arrange the normal and the anomaly to be in the same data location. And for it to be in the same data location, we gave it the data frame, we gave the data frame title, which is the timestamp, power consumptions, normal and anomaly. And then we save it as a CSV file, giving it a name as a CSV file. Then after saving that, then the next thing is to now use that data that has been saved. And to do that, we read the data, we define the X variable, and then we bring in the isolation forest. The isolation forest will now help us to do the detection of a normal and anomalous situation, and then we plot our results. And that gives us something like this, where I use the red dotted lines to stimulate anomaly and the normal signal to represent the power consumption data from the synthetic data. So this is a typical case where you want to differentiate anomaly from normal. But there's something you have to be careful here. If you end your result here, you may not be able to know whether your isolation forest was performing good or not. And that is why we try to always check the metrics. And to do that, we run the metrics. So to run the metrics, we run the accuracy, precision, recall, F1 score, confusion matrix, and the rest of them, the classification report. And to do the classification report, we have this kind of result. And you can see in this result, the accuracy is 97. But if you close your eyes to accuracy, try to look at F1 score, precision, recall, you will see that it's exposing some poor performance. For example, you could see that the isolation forest was able to classify 16 normal data are still being classified as anomalous data. So because of this, I tried another model apart from isolation forest. Before that, I just tried to play around with explainability with Sharp. So to play around with explainability, install my Sharp, import my Sharp, and use my Sharp to unravel the basis of the isolation forest results. This is just not part of the discussion. I just brought it. I wanted to investigate the feature values that was used by the isolation forest. That was why I did Sharp explainability. Then we tried one class SVM. In one class SVM, I screenshot it here. thank God I've screenshot most of these things. Otherwise, I didn't see how my collab just disappeared, and I don't want to waste my time. So we bring in the one class SVM, we run it again, and in this case, you could see that the result was even poor. Result was even poorer when compared to Isolation Forest. And these are the results. So you could see that the one class SVM had 303 normal data being classified as anomalous, which is terrible. I went again to try yet another one. And in this case, I tried random forest. Random forest gave a more better result. For example, you could see that while we were battling with 16 and 303 wrong classification for normal versus anomalous, here we had just one. And we even reduced this side from 25 and 12, we reduced it to 4. Why this was increased from 21 and 34 to 42. So in this situation, if we had to put the three results side by side, we could say that random forest performed better than the both one class SVM and one class SVM and isolation forest, as the case may be. Yeah. So meetings about attacks and information technology. Okay, I'm going to answer that later. So we move on. Now, in the first class of today, somebody asked a question that can we work online? So I want to use the second example as a case study. Now, this data set is online. This data set is on the UCI machine learning repository. If you are students and you're working on AI and machine learning research, please, this is a repository that will be very helpful to you. It has so many data sets. And then the good thing about it is that some of the data sets also have a lot of communities. What I mean by community is that when you pick a data set, you could see that a lot of PhD students, a lot of researchers all over the world, they've been trying to do a lot of things with that data set. So sometimes the community can help you to navigate your way if you are using a popular data set. So today, I want to use this data set known as RTIOT 2022 dataset. It was uploaded in 2024, 1st of April, January 4th. And this is the link to the dataset. When we have such a thing, what do? The first thing you do, when you click on, if you upload this link, this is what you will see. You will see UCI machine learning repository. Then you could see here, it says download dataset. Now, for some of us, now I don't have a problem because when I was in South Korea, I had a lot of resources for research. When I came to the US, the same thing. But when I was in Nigeria, I didn't have the resources. So we have to learn the hard way. Now, if you download this into your computer, it's okay. But for me, why do you want to download it when you can go to the next one? The next one says import in Python. So when you click on import in Python, then you save yourself the stress of putting the data set in your computer if you don't need it. So when you do that, you just install the UCI repo package in your Google Colab. Then you now, once this is fully installed, then you can link yourself, your Google Colab, to the dataset online without downloading your dataset. Then we can proceed with the research work. Let me see if I can share my I hope this one too. Okay, yeah, it's here. Yep. So when I so when I go to that UCI website, I click on the import as Python, then you take the code. You take the code, which is a pipe install repo. Then the next code is the one that will help you to link to the dataset, which is this one. Then you have your dataset output. Then you can now proceed to do whatever you want to do with your dataset. In this case, I want to do isolation forest, and then I want to use the standard scalar for the pre-processing, and I want to use the sklen for my train test splitting, depending on the ratio of your splitting and according to whatever research you are having in mind. So we do the splitting, we did the because of the categorical data that if you do the DH head, if you do data head, you see that there's some categorical data. So because of that, that was what led to the issue of one-hot encoding and all that. And then we encode the features and then put our data frame, drop any categorical column that we feel will not be useful to what we are trying to do, then do the splitting of the data, and then we go ahead to implement the isolation forest and plot the outcome. So this is the outcome of the output of the work. And this is my confusion matrix. And then this is my distribution of anomaly score. In this case, you could see that it is skewed. It is skewed in one side, which is also a cause for concern. If you are very good in, statistics, it's a cause for concern. And you could see in this side where I try to use Gemini to create some hypotheses and try to understand some hypotheses. That's what I was trying to explain to you. So you use Gemini to create hypotheses and understand the hypothesis, and sometimes Gemini will give you suggested changes. So I always caution, please, even Gemini also tell you, you can see here, see what he wrote here. Gemini also caution you. He say, use code with caution. Now I'll explain to you why this is important. This is very, very important because the fact that you are using Gemini to assist in yourself does not mean you lose track of your research. So it means that even when there are suggested changes, you also have to confirm if that is what you want to do. Otherwise, you ignore or you prompt again for a better suggested changes. And then, so we try the isolation forest. Then I also tried the random forest classifier, and that gave a better result, a better outcome that is not so skewed compared to the other one. So with that now, I did everything I could do without any need of having my data set in my system or offline or whatever. So just link yourself up with the UCI repository, and that is how it's also is most repositories. You can also always have a way to link yourself with some of the repositories, and then in that case, you may not necessarily need to bother yourself about having your work in your system and all that. So random forest classifier, and then gave a better results. So thank you very much, and let's keep in touch. Now let me go to the comment section and see if I will answer questions. The first person says, what is the difference between cyber attacks in IT and OT? Okay, good. So yesterday, yesterday, Professor also answered this question, if I remember, because I was in that class. In order to know the difference between the cyber attacks in IT and OT, we have to agree what is IT, what is OT. Operational simply signifies the components that make up the platform. I want to believe that IT and OT being referred to here, maybe example is smart grid. Let's say example smart grid. So if you say the OT of a smart grid, the OT of a smart grid are the components, equipment, devices that are making smart grid to behave and function properly. So your smart meter, your AMI, your advanced meter instrument, your PMU devices. These are your OT. But when we say IT, information technology, we are referring to the connectivity tools and software that are making one OT to interact with another OT, or one part of your grid to have a communication with another part of your grid. Therefore, what is the difference? What is the difference between cyber attack of OT and IT? Now, if you attack this device I'm holding in my hand directly, maybe you attack it by making it to stop functioning. Say you made it to be that I ended up downloading a virus into this my laptop, and this my laptop is part of my grid. Now you have attacked this advanced meter instrument, so it's a cyber attack on the OT. However, if what you attacked was the advanced meter instrument is supposed to send a meter report from my consumer building to the utility office, and then you made it impossible for my device to send a instrument from, it's still working. The meter is working in my house, it's taking measurement, but there is no means of communicating again. You have attacked the communication link. You have broken down the link between my consumer and the utility office. You have attacked the IT infrastructure of that company. So there's always a very a blur line between a perfect distinction between cyber attack in IT and cyber attack in OT, because one can lead to the other. I give you an example. If I develop a network, a computer network, and physically somebody went and burned a server, physically, you burn a server physically, that is an attack on OT, but it may not be a cyber attack. It's a physical attack, but it has also led to a breakdown of IT infrastructure. So cyber attack to IT refers to as cyber attacks to whatever prevent the smooth operation of the software or communication protocol aspect of a scenario. So in this case, let us look at a smart grid. So if you are attacking my communication protocols, if you are attacking my IT infrastructures, devices that are enabling communication from one point to the other, you are doing a cyber attack on my IT. If you are causing a denial of service to my network or to my web application, you are preventing the operational dashboard of the utility company from seeing the actual result, or you are corrupting even the results. Say, for example, there is a breakdown of grid, but you are able to deceive the operational office to be seeing that the grid is working fine, even though the grid has stopped working, but the result that is showing in the dashboard is showing that it is still working. So you have used some virus or ransom devices to hijack the system and make me to think things are working when things are no longer working. So in that case, you are attacking the IT. So to summarize my distinction, cyber attack on OT simply imply an attack on the devices that make up the grid. So any form of way you are able to pull down the AMI from working, any way you are able to prevent the generators from working, any attempt, anything you are able to do to prevent the things that make up the grid from working, then we can say you are attacking the OT. But anything you are able to do to prevent the devices from communicating, from interacting, from sharing appropriate data with one another, then you are attacking the IT. I don't know if I satisfy you in my explanation. I try my little best. Do we have more questions?
Yeah, Dr. Cosmos, I have a question here. If we say here anomaly detections via machine learning or any kind of physics error algorithm, are all these anomaly detections kind of real time or?
Okay, so the real-timeness or otherwise of whatever we are trying to discuss, you see, I want us to understand. Luckily for me, the last lab I work in South Korea is real-time lab. The name of the lab is Real-Time System Lab, and a lot of people have tried to misunderstand when we say real-time. Real-time simply means that you are discovering on the go. So if you are talking about real-time, then why are you talking about dataset preprocessing? Why are you talking about dataset normalization? Why are you talking about going to download dataset from IEEE data ports? It's no longer real-time. If it's going to be real-time, it means your devices will be working and they will be generating data, and you will be receiving that data as input into your machine learning. And then you run whatever you are running on the spot. That is what is real-time. Take, for example, when you go to ChatGPT and you prompt ChatGPT, you get your response, right? Immediately.
Yes.
You don't drop your point in ChatGPT and then you say, okay, ChatGPT say, okay, come tomorrow and get the results. No, you get the results maybe 5 seconds later, or maybe 10 seconds later, or 15 seconds later. That is near real time. That is real time. So, so if you are interested in a real time machine learning or real time classification, it's doable, but it means you have to set up your test bed. You have to set up your test bed. Then your test bed must be set up in a way that will guarantee the output of your data becoming the input of your machine learning, which we cannot do in this class.
Okay. Okay, it's so well explanation because I
Yeah.
had a doubt, so you have cleared it very well. Thank you.
Somebody said the provided Google slide is asking for access request. Oh, sorry. Let me see what I will do. Okay. Okay, so so for the access request, I think you should just discuss with the organizers. I don't have the right to remove I don't have the right to give access for now. So facilitators will be able to resolve that.
Yeah, maybe we can contact with you and later and give
Yeah,
access to the
yeah.
certificate.
Okay. Then this person says, which cyber attacks are most dangerous in smart grid and microgrid, and which new attacks should be addressed? So, um, to answer this question, the the cyber attacks that are considered more dangerous differ from country to country, and I will tell you why. Um, as a matter of fact, cyber attackers don't attack if they don't have anything, if there is no motive and there is no, if there's no motive and there's nothing to gain. So in some countries, they don't even battle about cyber attacks; they're battling about physical attacks. But let us look at some power nations like the United States, for example, some power nations where they have to be conscious, continuously conscious because of the position they occupy in the world. The cyber attacks that can be considered problematic, which has been attracting research attention, is false data injection, for example. In fact, a lot of papers are continuously being written on false data injection as a popular and trending attack type in the smart grid and microgrid. Another one is the problem of denial of service. Denial of service attack, especially the distributed denial of service attacks. And then one of the things people try to do of recent is what we refer to as hijacking of the AMI, the Advanced Metering Instrument. One of the ways some attackers try to do what is called a ransomware attack of the AMI and then cause a lot of financial problem to the utility companies, because if you cannot estimate what your consumers are consuming, you cannot build them. And if you cannot build them, you lose a lot of money. So if you can do a ransom hijacking of utility companies and the ability to bill their customers, then you now tell them a stipulated amount of money they are going to pay before they can be allowed to resume business. So the companies look at the billions of dollars they are going to lose, so they negotiate the ransom and then they are freed. So is it more dangerous? I don't know. But I know that it can only be most dangerous if it can lead to most loss of lives, or if it can lead to most loss of hours of power provision. So what is most dangerous may differ. And then which new attack should be addressed? Which new attack should be addressed? I may not have a very sincere, I may not have a very good answer for you in that regard, because these guys are not sleeping. So we have to just rely on McKinsey reports. We have to rely on trends and keep reacting and keep coming up with solutions as attacks continue to happen. I cannot say this is the new trend because we don't even know what they are planning right now. So can attacks like replay and occur in? Yeah. So what is distributed denial of service? It simply means preventing an operation from moving forward by flooding continuously IT. So DDoS is an example of IT attack that also have effect on the OT. So it can occur because you have to understand when we say grid, remember, we are not referring to the traditional grid. I think I have to make that very clear, because for example, if I'm explaining if I'm explaining smart grid to electrical engineering students in remote part of Nigeria, he will not understand what I'm saying because there is no smart grid. Most of the grids in Nigeria are traditional grid. So if you are telling him about DDoS attack, it doesn't make sense to him. Because how can you cannot do a cyber attack on something that is not having a cyber event, right? So to answer your question, can the attacks like replay and DDoS occur in grids? The answer is yes, if the grid is a smart grid. But if the grid is not a smart grid, then the answer is no. Because you cannot have a cyber attack for a non-cyber event. If your grid is traditional, non-smart, purely analog, nobody is going to, no virus is coming. If you don't have a computer in your house, why are you afraid of virus? If you don't have internet in your house, you cannot be afraid of anybody attacking you, right? Because if you're not connected to the internet, you're not connected to anywhere, you are not connected to anywhere, so nobody can attack you. That's why people say the best way to prevent cyber attack is to be disconnected. That is just on the joking side. Is the best way to prevent cyber attack is to disconnect yourself from the world. But how can you disconnect yourself from the world? This modern era, we can't do that. Yeah, so I enjoy answering questions, so that's why I try to make sure I have a lot of time. We still have more time, so let's have more questions if there are questions.
Good evening, sir. My name is Akash, and I have a couple of questions. And
Yes, sir.
before that, I would like to it was a really lovely presentation and very insightful. So my first question is like if we talk about the distribution side, and if we go to the end side, if we talk about the smart meters. So nowadays, smart meter is having a lot of technologies. So if we want to model those meters in the distribution domain and we want to apply some kind of cyber attack in that, so is this a like we can change or manipulate the values of power consumption, and can we consider it as a cyber attack?
Okay, so now you can only consider it as a cyber attack if you have a good problem formulation. And if you do a problem formulation whereby you are trying to explain the intention of the attacker. So if the attacker's intention is to manipulate the meter reading in order to deny the utility company from getting their money. Okay, let me give an example. If you want to say that when there is no attack, the meter reading is $2. But with attack, the meter reading is now $5 or it is $20, making the consumer to pay more money than they're supposed to pay. In that case, you are trying to use the meter reading as the evidence of attack. That is okay if you are doing if you are trying to explain that the motive of attack is to manipulate the reading of the meter. That means you are not modeling the attack, you are only modeling the outcome of the attack. It's not
And
the
can
attack.
we do
You are only modeling you are modeling the outcome of the attack. So in that case, you are going to have a data set of the meter reading that is correct and the meter reading that is incorrect. Then you now do anomalous attack. But if you look at it critically, sincerely, you cannot say that was actually a modeling of cyber attack. In fact, one of the papers I reviewed 7 months ago, last year, July, the author he did this, he did exactly what you have said. And personally, I recommended the paper to be rejected because my argument was that changing the amount of the data or meter reading does not mean an attack, because a meter reading can also change because the meter is not functioning properly. Even though there's no attack, a meter can be malfunctioning, and then because it is malfunctioning, it's having a wrong data, but it was not because of any cyber attack. So if you say, oh, whenever the meter reading is wrong, then there's cyber attack, it's not very correct. But like I said, in research, if you put assumptions, if you say in this research, we assume an attack based on the following situation. One, we assume that the meter is working fine. We assume that the connectivity between the company and this is. So when you put those assumptions, then you establish the attack according to your assumption. Then I can agree with you based on your assumption, but not based on general assumption. No.
Okay. Thank you for this. Similarly, if we go a bit if we go ahead, then this is a fundamental rule that whenever we are increasing or decreasing the load, the voltage is being varied of the each and every node. So, for example, if attacker has reduced 50 percentage of load, or attacker has give some kind of man in the middle attack or some kind of attack, or maybe it is for false data injection attack. So overall idea is just to reduce the 50% of load. So once the load is being decreased, automatically the voltage variation is going to very high. So will it be considered it is a cyber attack, or then my question is, how do we differ from the physical system? Because there might be a possible that one line is out of service. So in that scenario, the same outcome we will be getting.
That is what I'm trying to explain now. Cyber attacks is more of IT protocol scanning, but what you are explaining is more of OT. And it's difficult to conclude on anything when it comes to OT, because OT can be because of cyber attack, OT can be because of non-cyber attacks. Malfunctioning of OT can be because of both non and cyber attack issues. So it's difficult. It's a complex situation to say this is the major assumption. That is why some research in grid are not properly done just by assumptions and simulations. Some research in grid are best done when you collaborate with utility companies. That's like in SG Real, in our lab here in the US, most of our research work, we collaborate with the utility companies, because when you collaborate with utility companies, then it reduces your too many assumptions, because you are working with the real situation, the real life situation with the companies, and then you can give you a better quality of research output. But if it is just classroom work, then any assumption that is agreed by everybody is okay for purpose of classroom, but in real life, it may not work.
Sir, one another challenge which we are having from starting onwards, that bad data. So we have a techniques to detect bad data, and we have been using what it is called WLS state estimation, or maybe Kalman filter, and many more. So my question is, if we are able to detect bad data, which is present in the system, the data which we are getting from the SCADA system, or maybe smart meters. So my point is, if we go ahead and if we put one stage, one for the better data, or we can say one stage for the WLS estimation, and then after if we use the neural network, then after we can use the power of artificial intelligence. So will it be helpful for us?
Yes, perfect. That would be very helpful, because now you can now associate the bad data as anomalous situation, and then the good data as a normal situation, which is beautiful. If you check this paper, this Denoising and detection of bad data in distribution phasor measurement using filtering, clustering, and Koopman mode analysis. You will appreciate what I'm trying to say. This paper is also from our lab. Yeah.
Yeah, sure, sir. Definitely we'll go through with this. All right, then one another question is, for example, we have a IEEE 14 bus test system. Okay, let's say we have a IEEE 33 bus test system with a distribution system. So we have a 33 nodes. Simultaneously, we have a 3 or 4 parameters for each and every node, like voltages, angles, power injected, active power injected, and the reactive power injected. So each and every node is having 4 components, 4 parameters, and the line which is connected, these two nodes are connected with line. These lines are also having similar kind of parameters: P flow, power flowing, active power flow, and the reactive power flow. So according to this, we have around 4 to 6 parameters. So how can we give this data set to the neural network? This is the big problem, a big challenge for us.
Yeah. So 2 things you have to have in mind. Do you want to do physics informed AI? If you want to do physics informed AI, the first thing you have to do is the parameters is their equation that connects them together, that make them to have interaction. If there are equations that make those parameters to have an interaction, then you are on the journey to physics AI. And that will solve your problem of connecting data for a complex situation, because that's the purpose of physics informed AI. That's the purpose of physics informed AI. But the major problem is, first of all, is it possible to change the scenario into mathematical equation relationship that can become the basis for your physics, the physics law and constraint? Then that physics law and constraint become the tool that will be used to generate your synthetic data that become the input of your physics informed AI. So the problem of physics informed AI is that most successful physics informed AI research, you have to collaborate with mathematicians, or if you are good on your own, that's wonderful. Otherwise, you have to collaborate with mathematicians to come up with the physics of the relationship before you can proceed to the next level of physics informed AI.
All right, sir.
Yeah.
Thank you so much for your answers.
You're welcome.
We would love to stay in touch with you, sir, in future also.
No problem, sir. You can always get my information from the organizers, or you just let me see. Yeah. So I dropped my email, but if you have to have anything, you can always interact with the organizers, or you just, once you send any message to my professor will always contact me.
Yeah, sure, sir.
Okay. If there is no questions from the participants, maybe we can end today's course. Okay. Thank you, Dr. Cosmos, for your insightful course on this physics over artificial intelligence algorithms uses in the power systems, and letting us know the ongoing trends in the machine learning. And that is really a passionate lecture delivered by you. I think all participants have enjoyed the course. Yeah, that's fair. I wish you all the best and have a nice day.
Thank you so much. Have a nice day, everyone.
And
Thank
thank you
you.
for your time here for this course.
Thank you.
Appreciate.
Thank you, Professor Cosmos.
Thank you, sir. Thank you, Prof.
Thank you so much.
And
Have a
thank you
good
for
day.
accepting my connect on LinkedIn.
Yeah, no problem. Thank you, sir.
Yeah,
Thank
thank
you,
you,
sir.
Prof.
Take care.
All right, take care, everybody.
Yes, thank you.